All right, grade 10s, we are going to start learning about ionic compounds. If you don't know what those words mean, well, we're going to learn them. So an ion is an atom which has lost or gained an electron from its normal state. Now, you already know how to figure out how many electrons an atom normally has. That's what you've been practicing last week. And so if an atom has a different number of electrons than what you might expect, then it's called an ion. And a compound is two or more atoms which come together as a chemical bond as a result of a chemical reaction. So when you squish two atoms together and they stick together and fly around in space as a pair or as a trio or a group of atoms stuck together, that's a compound. Ionic compounds form as a result of a chemical reaction. You know, when you mix stuff together in a beaker and you get two different liquids mixing together, they form compounds, that sort of thing. So an atom is happy when its outer shell is full of electrons. And when we say full, that means there are no more that can fit. And different shells have different capacities. So if you look on this is argon. Argon has 18 electrons, but they come in different rings. So the first two are these two, 1 and 2. The first two electrons that go, if you're going to build argon, you would start with these 2 electrons. Now that inner ring only has 2 electrons. And then the next 8 you put onto the second ring, and we call that a shell. So the second shell can hold 8 electrons. And then the third shell can also hold 8 electrons. And the atom is happy if the outermost shell, which in this case is this third one, if it's full, completely full, then the atom is happy. Oh, look at it. It's having a nice little snooze. So if there's only one shell, for example, helium only has 2 electrons. And so it only has one shell because that shell can fit both of the electrons that helium has. Helium's happy because its outer shell is full. Neon has 10 electrons, and so the first 2 go into the first shell, and then the next 8 go into the next shell. And neon is happy as well because its outer shell is full. And here's argon, which we just saw. Argon is also happy because its outer shell is full because it can hold exactly 8 electrons. If it had any more electrons, it would have to have another shell, a fourth shell. So you can think of atoms with a full outer shell as being satisfied and calm. They're just, they're having a little nap. They're not outside running around. Zzz. See, this argon is having a nice little nap. So comfortable. So in this state, if the outer shell is full, it will not react with other atoms. So if you mix argon with a bunch of something else like chlorine or potassium or something, it's not going to mix with it because argon is happy the way it is. It doesn't want to go strike up a friendship with another atom. It's just happy to be by itself. If you have an atom with an outer shell that is not full, then it's not happy. Magnesium, for example, if you look at the outer shell, there are only 2 electrons. But that third shell can hold 8, and so it's not full. And so magnesium is not happy. It's not satisfied. It's not calm. And so magnesium is going to try to react with other atoms so that it can fill up its outer shell. And we're going to figure out how that happens. Magnesium is clearly not happy, as you can see from the speech bubble. Potassium, this is potassium with the symbol K. Potassium only has 1 electron in its outer shell because in total it has 19 electrons. So we have 2 and then 8 and then 8. That makes 18 in total, but it has 1 more, so it has to go into the 4th shell. So potassium has 1 extra electron in its outer shell. It's so close to having a full outer shell. If only potassium could just lose that 1 electron. If potassium could get rid of this electron, then it would only have 3 shells, and the third one would be full, and potassium would be happy. Here's fluorine. Now look at fluorine. Fluorine, in its outer shell, has 1, 2, 3, 4, 5, 6, 7 electrons. Remember, this shell can hold 8. So if fluorine had 1 more electron, it would be happy. You can probably see what I'm getting at here. Fluorine is only 1 electron short of a full outer shell. Meanwhile, potassium, we remember, has 1 extra electron. If only they could get together, right? Too bad. So, could the two atoms work together to get what they want? And what they want, of course, is a full outer shell of electrons for each of them. And the answer is yes. So the extra electron there that potassium has can go there to fluorine. And now look, their outer shells are both full. Fluorine has the second shell is full. Potassium gets rid of its fourth shell because there's no electrons in it anymore. And so its third shell is the outer shell, and that shell is full. But what happens is when potassium gives its electron to fluorine, they get stuck together. So they don't go off and go their separate ways. They actually stick together, and then they just travel around attached to each other. And this is called an ionic bond. They are bonded together, and they are both ions. Remember, an ion is an atom that has lost or gained an electron. Fluorine has gained an electron, so it's an ion. Potassium has lost an electron, so it's also an ion. These are both ions, and they are bonded together, so it's called an ionic bond. And this thick line represents the bond. It's basically showing you that they're stuck together. When you have an ionic bond, there is always a giver, and that is a metal. So potassium is a metal because it's giving an electron away. And there is always a taker. The atom that takes an electron is a nonmetal. Ionic bonds always have a metal and a nonmetal. And this is the same thing we just saw. So now fluorine actually has a negative charge because it has an extra electron. And remember, electrons are negatively charged. And potassium has a positive charge because it lost an electron, but it still has all the protons. So it has one more proton than electrons, and so it has a positive charge. And so they stick together because when you have a negative and a positive, they attract each other and they stick together. And so that's actually how they bond. That's how they form their ionic bond, is through the negative and positive attraction between electrons and protons. So here's a picture of the periodic table broken down by metals and nonmetals. So generally over here on the right is where you see the nonmetals, and most of the rest of the atoms or the elements are metals. And a lot of the ones you might expect, many of these things you've never heard of, obviously, but some of them are common. Like, for example, you've probably heard of nickel. Nickel is a metal. You should know that. Cu is copper. You've probably heard of copper. That's a metal. Down here we have gold and silver and platinum. And let's see, Pb, whereas Pb is lead. These are all things you should have heard of, and you should definitely be thinking to yourself, oh yeah, those are definitely metals, because when I picture them, they look like metals. Whereas some of these other nonmetals like oxygen and neon and helium, obviously we encounter those as gases normally, and so they don't really seem very metallic. So generally, which ones are metals and which ones are nonmetals makes sense based on your life experience. And then we have a few in here in the middle that can kind of swing both ways. They're called metalloids. In some cases, they can act as metals, and in some cases, they can act as nonmetals. Okay, so in terms of naming the compound, we name the metal first. So you want to think of the metal. In this case, the metal is potassium. And then the nonmetal goes second. And you change the ending of the word so that it's IDE. It's always IDE on the end. And so this is potassium and fluorine. But remember, we take the nonmetal and we change the ending to IDE. And so it's potassium fluoride. So this is potassium and this is fluorine, but when they stick together and form an ionic compound, that compound is called potassium fluoride. And the symbol for potassium fluoride is Kf, because K is potassium and F is fluorine. And there's one of each of them. That's important. We're going to see examples where that's not the case. There might be multiple copies of one of the atoms. But for now, with this one, this is the simplest possible version. We just have one of each, so it's just Kf. Let's talk about something called Lewis dot diagrams. If I go back to this last slide, every time you draw an ionic compound, it's annoying that you have to draw all of this stuff. Like, it's a pretty extensive diagram to have to draw. So we have a simpler diagram called a Lewis dot diagram. Remember, this is called a Bohr-Rutherford diagram, but a Lewis dot diagram is much simpler. It only shows the electrons in the outermost shell. It doesn't care about the other electrons, because those inner electrons don't affect how atoms bond with each other. So Lewis dot diagrams are much easier when looking at bonding. This is the Bohr-Rutherford diagram of potassium. This is the Lewis dot diagram of potassium. Look how much simpler it is. And so what does this mean? Well, first of all, K is just the symbol of potassium, and then there's one dot. All that means is there's only one electron in the outer shell of potassium, and it's not showing the electrons from the first, second, and third shells because they don't matter in terms of bonding. All that matters is how many electrons are in the outer shell, so we just draw one dot, and that's so much easier. Here are the first 20 elements with their Lewis dot diagrams. Now, I'd like to go just for a moment over to p-table, our best friend, our favorite periodic table website. So if you're trying to figure out how to draw a Lewis dot diagram, remember, if we look at period number 1, that's row number 1, hydrogen and helium, there are only 2 elements in period number 1, which means that the first shell can only hold 2 electrons. And so then when you go to the second row, that's when you start the second shell. And so if you look across the second period, you can see that there are 8 elements. And that's why the second shell can hold 8 electrons, because every time you go to the next atom or the next element, you add one more electron, and then it fills up by the time you get over here to neon. And then when you go over to number 11, sodium, you start the next shell. This is the third shell now, and the third shell can also hold 8 electrons. And it gets more complicated after that, but we're basically going to stick to the first 18 to 20 elements. So that's really all you need to know. So for example, if I'm looking at, say, silicon right here, you can see the Lewis dot diagram has 1, 2, 3, 4 electrons in it. Well, let's see how that works on the periodic table. Silicon is here. So if I count up from sodium has 1 because it's in group 1, 2, 3, 4. So silicon has 4 electrons in its outer shell. Now, just be careful. It's in group 14. That doesn't mean it has 14 electrons in its outer shell, because remember, there's this big gap in the middle here. There are no elements between magnesium and aluminum. So you'd have to count from the beginning of the row going across. 1, 2, 3, 4. Silicon has 4 electrons in its outer shell. And you can see the Lewis dot diagrams for all of the first 20 elements here.